1, 2, 3, go.
Yeah, so don't really have time for a special intro now. Got stuff to talk about, things to do, a lot of things to drive. So I kind of wormed my way into the reaction engineering course as well, video series. So just to set the record straight, this is heat and mass transfer. And basically what we're going to be doing is applying Fourier's law to surfaces that are not flat, which should be fun. So this is a cylinder. Let's actually just draw a little bit more, draw it out so you can tell it's a cylinder. Like so. Okay? And basically what we're going to be doing is taking a differential area like that. Well, it's actually a volume. Yeah, it's a volume. So in case you can't see it, there's two dashed lines here. So we have a DR. And what we're going to be doing is doing an energy balance. So, that looks awful. So we're just going to be balancing the heat coming in with the heat coming out. Normally it's energy in, energy out, but since we only have heat, it's kind of a moot point. Now, since there's no generation and this is all steady state, one-dimensional, we can pretty much say that Q at radius R is equal to Q at radius R plus delta R. Meaning that if we shift this over to this side, we can have or is it, maybe I flipped it. Oh well, doesn't really matter. Equals 0, we can divide by delta R and get it into a limit notation. As delta R goes to 0 of this difference. Again, I'm not entirely sure if it should be R plus R, delta R minus Q at R, or the other way, but it doesn't really matter because we could just divide by negative delta R and get the same thing. What is important is that we find out that this is a derivative, dQr dr, which is equal to 0. Meaning that QR is equal to some constant. So we kind of expect that because we're not adding any heat, so the heat flow is going to be constant. So pretty much what I'm going to do now is I'm going to bring this up here and say, well, why do we care? How does this relate to Fourier's law, which, in case you've forgotten, is right up there. It's dr instead of dt because we're looking at heat flow in the radial direction, so we want the temperature differences in the radial direction as well. So what we're going to do here is just recall that this heat flux is just the heat flow divided by an area. Now, in the flat wall examples, we didn't really care because the area was always constant. I mean, we draw ourselves a little wall for reference. Let's look. If I take the volume here, I'm really just rushing through this, it doesn't really matter. But it doesn't matter where along the cross-section of this box, the cross-sectional area is always the same. So it's a constant, so the heat flux or the heat, it really didn't matter all that much. But you'll find out that because the radius of the surface area of the cylinder is changing as you increase the radius, you have to take it into account. So what we're going to do is just do QR. The surface area of a cylinder is 2 pi RL is equal to delta T dr. So we're going to just do a little bit of magic. Yeah?
Problem 2, do we have to solve for T2 and T5?
What's problem 2 again?
The one with the 4.
You have to solve. You don't really have to solve for any temperatures because just need to make equations where you can find the different lengths. Because they give you the temperatures you need. And if you can, because all you're just doing is you're going to find a place to start and a place to stop your heat flow.
Okay, yeah, that makes sense.
So it doesn't really matter where you start and where you stop. But that's irrelevant to this lesson. So back to what we were saying, we have the heat flow divided by 2 pi L, right, we're rearranging our variables, that's what we were doing. So that, oh, sorry, no, that's wrong. We're multiplying by dr in order to get, that d does not exist, to get this, effectively. So now we're just going to integrate along the 2 radii that I've got drawn out here. So if this is our center, we have an inner radius, and we have an outer one. Again, it's very hard to tell, but there are 2 circles there that are concentric, so pretty much you have an inner radius and an outer radius. So Ri and Ro. We can do the same thing with the temperature, assuming that K is constant, we can just pull it out and do this. So QR 2 pi L times integral of this, well, when everything's said and done, it's the natural log of RO over RI, which is equal to negative K. Same thing, TO minus TI. I'm just going to absorb this negative sign in there. So it goes to said I was going to absorb that. Ti minus To. And so pretty much what I'm just going to do is solve for QR. Although, if you're trying to do a multi-layer cylinder, you have to do a very similar process to what we did in the multi-layer flat wall case that I also did, where we added up all the different equivalent heat flows, and then just, well, yeah, it's probably best if you just look at that video. Which lecture was that, Sahib?
I think that's the one right before this one, right?
Is it right before this one? I thought that you have one in between them.
The one that, you mean the one that I'm doing, Jared, right now? Oh wait, you're working on this one. Wait, what was your question?
I'm just asking, which lecture, what did we call the lecture where we did multi-wall heat transfer? Multi-layer flat wall heat transfer.
Oh, multi-wall level, that was lecture 4.
Lecture 4, because basically it's the same process. That
aren't I in charge of lecture 4?
Are you? I could have swore I did
Did you do multi-wall?
Yeah, I did. You did single wall.
Oh, so you're doing multi-cylindrical wall right now?
I'm not doing the multi part, because basically it's just...
It's the same thing.
It's doing the same thing. I'm just deriving how to get the heat flow.
So I'm going to be doing one-dimensional heat conduction and spherical walls.
Wait, no.
Yeah.
What?
I'm doing this shit. It's fine. They don't care.
I know, but Saheba, I thought that was all the same lecture.
No.
Oh, no, you're right. It's
yeah, don't do my part.
crap.
Don't do spherical wall or one-dimensional heat conduction.
Oh, wow. That's embarrassing. I rehearsed I was going to do all of that, but... Okay, then. I guess that's everything for me.
Yeah, it is.
Wow. That took way too much time in class.
Yeah, it did. Did you tell a story or something?
I don't even know. The camera's still rolling, but still.
Yeah, I don't care.
Still. Damn. Either I just broke the world's record for speed talking or what?